Differential equations, we're in section 4.7, the last section of chapter 4 for us, but we're going to spend several days on it. Day 1, we're looking at homogeneous Cauchy Euler equations. Our right-hand side of our differential equation will be 0 today. But you very well could be asking, what is a Cauchy Euler differential equation? And how do we go about solving them? Well, here's the key. The degree of x will be the same. It will be equal to the order of a derivative for each and every term. So, for example, if you had the nth derivative of y multiplied to that as a coefficient, you'd have the nth power of x. When you get to the second derivative of y, you have x to the second power out in front. And that will be true for every term in this differential equation. So let's take a look at our second order. And really that's where we're going to truly be focused in today, really looking at that second order. You can see what is happening. What are we going to do to solve this? Well, it's very much going to run parallel to how we were solving differential equations earlier when we were assuming that y equals e to the mx might be a solution. Today with the Cauchy Euler, we're going to assume that y equals x to the m is a solution. And hopefully you're going to see that this is actually a very reasonable assumption. You'll see why in just a moment. Look what happens if you are assuming that that's the case. And m is some constant. We don't know what it is. But as we take our first derivative, you drop down your power. You'll have m times x to the m minus 1. Take your second derivative. Well, now you drop down another power. You'll have m times m minus 1. You got to subtract one more. You'll have x to the m minus 2. And then we substitute these in. And what's going to happen? Well, we're going to get right over here, we're going to have ax squared, but now that second derivative, you can see it's m times m minus 1, x to the m minus 2. We'll have bx, but our y prime is going to be m times x to the m minus 1. We have c times y, but our y is x to the m. And as you're looking here, you're hopefully going to remember something, that when we had x to the a times x to the b, that's x to the a plus b, a very basic property of exponents. What you're going to see is for all of these x's here, this is x to the 1, isn't it? You'll have x to the 2, x to the m minus 2. You add 2 plus m minus 2, that's just an x to the m. And everything else remains the same. Here, 1 plus m minus 1 is just an m, and all of a sudden you will very, very, very quickly see that your new equation, once you make that substitution, is going to have x to the m for each and every term. Now, we can look at this in two different ways. You could correctly divide every term by x to the m, and you'd have a greatly simplified equation. Or you could look at this as if saying, look at the right-hand side. On the right-hand side, looking at coefficient analysis, you'd say we have a 0 in front of x to the m, so everything in front of x to the m has to add up to a 0. Regardless of which approach you're looking at, which interpretation, you're now going to see that you would have am times m minus 1 plus bm plus c. And then we could just very quickly clean this up. And you're going to see that you're going to be left with a quadratic. Very similar to what we were doing earlier. And you could see in this quadratic, I could factor out an m, and b is positive, a is negative, and look at this. This is where we're going. This thing right here for a second order, without a doubt, is where we're going to revisit time and time again. As we proceed with these problems, you're going to see we're going to jump pretty much straight to here. And we're going to solve that quadratic much the way we did earlier in the unit when we were substituting y equals e to the mx power. What you can see is, once again, you could get three different types of solutions for your quadratic. You might get two of the same, m1 and m2. Well, look, we're assuming that x to the m is a solution. So you'd have c sub 1 x to the m1. But now look, in the past, we'd just throw an x out in front. Whenever we get a duplicate, whenever we've been putting x in the past, we're now going to replace it with ln of x. So that's very, very important. When we get the duplicate solutions, that x to the m sub 1 is going to have an ln of x multiplied in front of it for that second constant. If you have two different solutions, nicely, you're going to just come up with c1 x to the m1 plus c2 x to the m2. What happens when you get complex solutions? Well, you get complex solutions. Actually, I wanted you to look at what I'd written in B. Again, looking so amazingly close to what we were doing earlier in the unit. In the past, we'd have e to the alpha x. Well, we have x to the alpha, right? We've got x to the alpha. Wherever we have been having an x in the past, just like before, we're going to write it as an ln of x. So we'll have a beta ln of x, cosine beta of ln of x, and a sine beta of ln of x with those two different constants out in front. So with no further ado, let's jump in and see what these Cauchy Euler problems are going to look like. Obviously, this is like an x squared y double prime plus 0 y prime minus 2y equals 0. And what does that really mean? Well, we've got a 1 out in front of here. A would equal 1. B would equal 0. And c would equal -2. So this is going to help us as we're going about solving that quadratic. And, where we're going with this is, like we saw earlier, and I put all those red stars out in front, and I highlighted it in light blue. I'm talking about number 4 right here. That's really where we're jumping. And we're just going to plug this in. You plug in your 1, you'll just have an m squared. And then we'll have b minus a. Well, that's 0 minus 1. And then our c, of course, is -2. And my goodness, it does not take long to see that we have this. It does factor. In fact, I think it's going to factor rather nicely. I think you'd agree. We'll have an m minus 2, m plus 1, leading us to m is equal to 2, m is equal to -1. So what kind of an answer do we have? Well, we have a c1 x to the second plus c2 x to the -1, and we are done. Take a look at example 2. I think you can quickly see a is 4, b is 0, c is going to equal 1. And let's just jump straight in. These Cauchy Euler problems are going to go quickly. At the end of the day, you're really going to see that you are really just going to set this up and solve a nice quadratic. Here's 4m squared minus 4m plus 1. You can think, hey, does this factor? Indeed it does. It's a perfect square. I think you can see that pretty quickly. It's 2m minus 1 times 2m minus 1. What does that lead us to? Well, if you were to solve both of those, setting them equal to 0, you'd get identical solutions. Well, we'd have c1 x to the 1/2. But now this identical solution, the duplicate solution, in the past we'd always throw an x out in front of it. Remember, in this section with the Cauchy Euler, we're going to throw an ln of x. And we are done. Finally, as we look over here for number 3, we'd have a is equal to 1, b is equal to -7, c is equal to 41. And again, it's am squared plus b minus am plus c. Set that equal to 0. You'll have 1m squared. Here you get -7 minus 1m plus 41. And that's m squared minus 8m plus 41 equals 0. Now, with the 89, you could do a C-solve and get your solution. It would not take you very long to solve this by hand with your quadratic. A is equal to 1, b is equal to -8. I know that can look weird because we just had a b, and a c, but we'd have all of this right here, and we could say, well, the quadratic equation is opposite b plus or minus b squared minus 4ac all over 2a. And we'll have opposite b, well, that's an 8. And -8 squared for b squared, that's 64. And we just got to get this cleaned up. And 4 times 41, well, 4 times 41 is going to be 164. So this is 8 plus or minus 64 minus 164. And here, we can even bring this up here and say our m would be 8 plus or minus the square root of -100 all over a 2, which is really 10i. Divide everything by 2, we'd get 4 plus or minus 5i. That means alpha is equal to 4, beta is equal to 5. Now, please do remember what we have for our general solution when we have this very similar complex solution. You can see this is where we had x to the alpha c1 cosine of beta ln of x plus c2 sine of beta ln x. And guys, you can see we're virtually done. We'll have x to the 4th c1 cosine of a 5 ln of x plus c2 sine of 5 ln of x. And that wraps up day 1 of the Cauchy-Euler differential equation, the homogeneous form.